Okay, continuing with constructing confidence intervals. So the last two videos, the first one talked about like what a confidence interval is and gave an overview of the steps for constructing a confidence interval for proportions. This video is all about constructing confidence intervals for estimating a population mean. So instead of having a point estimate of p hat, we're going to be looking at x bar. We're going to need a different standard deviation, all sorts of fun stuff. So starting with, I already said the point estimate is x bar. To obtain a point estimate for the population mean, we can actually use the graphing calculator and that one variable statistics function. So we'll enter all of the data values into a list and do one variable stats to get x bar. So for example, we have the average reported miles per gallon of a 2007 Ford Taurus for 13 different owners is given below. We want to obtain a point estimate of the population mean miles per gallon of a 2007 Ford Taurus. All it means when it says point estimate is x bar, because it's an estimate of the population mean using a sample. So mean for a population is mu, the corresponding point estimate is x bar. So here are the miles per gallon. There's 28.5, 26, 21.7, 23.8. I typed all of these into list 1 in my calculator, did the one variable stats. Oh, there was a second row, sorry. And I got a mean of 23.92 miles per gallon and a standard deviation of 3.14 miles per gallon. Now remember, the calculator gives you two calculations for standard deviation. You want the one that's labeled S, not the one that's labeled with the Greek letter sigma. So the one thing that's different about this distribution is that we're not looking for a normal distribution this time. We're looking for a symmetric distribution. So we're going to estimate using what's called the student's t distribution. The reason this exists is because when you have sample sizes that are smaller than 30, they just don't quite match a normal distribution. So this distribution was developed. It is adjusted a little bit based on your sample size. So it's just a little more accurate. It's a better estimation, and we'll talk about it as we go through. Instead of using a z like the standard normal table does, now we're going to be using t for the t distribution. To calculate t, it's a very similar formula to finding z. Z is the sample estimate minus the population mean divided by the standard deviation. That's basically what this formula is doing, is taking your point estimate minus the mean divided by the standard deviation divided by the square root of the sample size. So it's a smaller measurement for the standard deviation. It's going to narrow the distribution a little bit. And we always use this measurement called degrees of freedom. The degrees of freedom is calculated by taking the sample size minus 1. Now, if you remember when we were calculating mean and standard deviation by hand, the standard deviation formula for a sample used n minus 1 in the calculation instead of the full sample size of n. So that's what the degrees of freedom is kind of tied to. Fortunately for us, StatsMate takes care of all of the math ramifications of that for us. So some properties, excuse me while I cough. Some of these are going to feel very similar to the normal distribution. The only thing that's significantly different is that the distribution itself will look a little bit different for varying degrees of freedom, but it's still centered at 0 like the standard normal distribution. It's symmetric with 0 in the middle like the standard normal distribution. The area under the curve is 1, same as the normal distribution. The area to the right of 0 is equal to the area to the left of 0. That's the same as the normal distribution. As the t-value increases or decreases, that curve, the tails of the curve are going to get closer and closer and closer to that horizontal axis, but they'll never touch it. That's the same as the normal distribution. But the area in the tails are slightly greater than the normal distribution. It's going to be a little bit higher off the axis just because of the way that the standard deviation is calculated. And as the sample size increases, the t-distribution gets closer to matching the standard normal distribution. You won't have to memorize these properties, it's just to give you an idea. If you want to see a picture of what the t-distribution would look like for different sizes, you can open probability distributions in StatsMate and go to the student's t-distribution and just play around with the different degrees of freedom. Just enter different numbers and degrees of freedom and see how it changes. We interpret a confidence interval for the mean, very similar to what we did in the last video about proportions. You still say I'm a certain percent confident that the population mean or average, so that's where it's different. We're talking about the population mean instead of proportion of whatever the variable is between the lower bound and the upper bound. So to figure out critical values in this case, so we're not looking for z, we're looking for t, but it's done the same way. We're still going to use StatsMate, and we're still looking at this alpha over 2 idea. T alpha over 2 is the critical value, so that the area to the right of t is equal to that alpha over 2. So like if I have a 90% confidence interval, that means the middle 90% of the t-distribution is what I'm looking at. The outer tails altogether are the other 10%. So the right tail is the one I care about, and it has to equal half of that 10%. So it has to be 5%. To calculate the t-values with StatsMate, you choose the t-distribution from your probability distributions, keep the area as upper tail, and you need to change the degrees of freedom part. The degrees of freedom is just your sample size minus 1, and then you enter the value of alpha over 2 as your probability. Whatever number shows up in the A box in StatsMate should be rounded to 3 decimal places, and that's the t-value that you use as your critical value. So here's just an example to go through. Make sure you have StatsMate open and verify that you get the same answer. If I ask you to find the t-value for a 90% confidence interval, assuming a sample size of 13. First of all, excuse the typo, it should be a 90% confidence interval. But first you want to pick the t-distribution from the main menu, keep the area set to upper tail. The degrees of freedom is n minus 1. N is 13 because it says a sample size of 13. 13 minus 1 is 12. The probability, this was actually the random example that I chose when I started talking about this in the last slide, but if I have a 90% confidence interval, that means there's 10% on the tails. I divide that 10% by 2 to get 5%. That's my alpha over 2 value. I type 0.05 as my probability, and in the A box, I get t equals 1.782, rounded to 3 decimal places. So that's how you find your critical value. The whole process of getting your confidence interval is similar to what we did last time. Instead of verifying the normal distribution, you're verifying the student's t-distribution. To do that, you just need to know that the original population is known to be normally distributed or symmetric. You want to figure out your sample size and then write off to the side your degrees of freedom by subtracting 1. You want to figure out your alpha and then the associated critical value using StatsMate like we just did. You need to know the values of the sample mean and the sample standard deviation. Typically we round to 2 decimal places. Those you get by running the one variable stats in your graphing calculator, or the problem will tell you what those values are. And to calculate the margin of error is similar to what we did last time. It's the critical value times the standard deviation for the distribution. The critical value is t for alpha over 2. The standard deviation calculation is the sample standard deviation divided by the square root of the sample size. Then the upper and lower bounds are calculated the same way that we did in the last video. It's the point estimate plus or minus the margin of error. The point estimate for this case is x bar for the sample mean, and margin of error we calculated in the last step. Then you interpret using the sentence on a previous slide. the example that I want to go through is just building off of that data in the first slide. So we want to construct and interpret a 90% confidence interval for the mean miles per gallon of a 2007 Ford Taurus, assuming the average miles per gallon is normally distributed. They needed to tell us that first thing, okay, because the average miles per gallon is normally distributed, we can use the t-distribution because they told us the population's normal. The sample size is still 13 cars, or 13 car owners, so the degrees of freedom is 12. Since we want a 95% confidence interval, we can't use that t-value we calculated in the previous example. If the confidence level is 95%, that means alpha is the other 5%. Divide that in half to get 2.5% or 0.025. Which I did incorrectly on here. So I'm going to pause and fix it, and my apologies. Okay, now that's all fixed up, it should have been the t-value for alpha over 2 being equal to 0.025, and when you enter that into StatsMate, you get a critical value of 2.179, which did have to get rounded up from 2.1788. Next, I already had the information from the one variable stats that the sample mean was 23.92, sample standard deviation was 3.14, so I can use all that information to calculate my margin of error. Margin of error is the critical value times the sample standard deviation divided by the square root of the sample size. I can type all that in my calculator at once, and I rounded to 2 decimal places because that's what we did for the mean and standard deviation, and I had to round up to 1.9. To calculate the upper bound and the lower bound, I just add and subtract the margin of error to the point estimate. So I did 23.92 minus 1.9 to get the lower bound, 23.92 plus 1.9 to get the upper bound, which lets me make an interpretation that we are 95% confident that the average miles per gallon for all 2007 Ford Tauruses is between 22.02 and 25.82. As before, we can actually get all of those answers directly from the graphing calculator pretty easily. If we entered the data in list 1, which you have to do to find the mean and standard deviation anyway, you can press the stat button, go over to the test menu, and you are looking for number 8, which is a t-interval, since this is the t-distribution, and it assumes that you're looking for a confidence interval for one sample mean. If you select the input of data, there's 2 choices there, data and stats. If you use data and your list is list 1, assuming that's where you put your original values, the frequency is 1, you're not multiplying them by anything. The C level is your confidence level. You want to just enter that percentage as a decimal, and you highlight calculate, press enter, and it gives you the answers. If you don't have the data in list 1, it's mostly the same steps, except your input is stats instead, and you type in what you know is your sample mean, you type in what you know is your sample standard deviation, and you type in your sample size and press enter. The answer is given to you similar to with the p-values. The graphing calculator shows you lower bound, comma, upper bound at the top, and it'll also give you the sample mean and standard deviation and sample size printed underneath it. Alright, so I'm sorry if there's a little bit of choppiness in there. I had to fix this and trying to work with the editing things, and I'm new to it. So anyway, the last part is figuring out the required sample size. If you have, if you're working with means, and if you want to make design a study as a researcher to figure out the correct sample size, you need to be able to do all of this math. To decide the sample size for the mean, we actually cannot use a t-value as the critical value because t is reliant on knowing the sample size for the degrees of freedom. So what we have to do is we just have to use the normal critical value as an estimate. That's our z value. So we find the critical value for z the same way that we did before using StatsMate, putting in our alpha over 2 as the probability in the normal distribution with a mean of 0, standard deviation of 1, and then whatever pops up in the A box is our z value. So the formula, there's only one in this case. Unlike with proportions, we had two different formulas depending on what you knew about your population. This time, the sample size would have to be a minimum of the z alpha over 2 value times the sample standard deviation divided by the desired margin of error, and that whole quantity gets squared. Don't forget you have to round up. You can't round down, otherwise you don't have quite enough. For example, if we just want to continue with the Ford Taurus thing, how large a sample is required to estimate the mean miles per gallon within 0.5 miles per gallon with 95% confidence. Again, when you see within, that's telling you your margin of error. And we have a confidence level of 95, so our alpha is 5%, alpha over 2 is 2.5%. So we're looking for z of 0.025, which we looked at in the previous video, and that's 1.96. The sample standard deviation we calculated way back on the first slide somewhere. That was at 3.14. And when we plug those numbers into the formula correctly, you have the 1.96 as your critical value times the sample standard deviation of 3.14 divided by the margin of error, and then you square that answer. What I did was I did 1.96 times 3.14 divided by 0.5, no parentheses or anything, just typed exactly that in the calculator, pressed enter, got an answer, and then I just pressed the squared button once the answer was on my screen, and then it shows answer squared. I got 151.51, and don't forget you have to round that up, so you would need at least 152 Ford Tauruses in your sample to be able to construct confidence intervals and move further into estimating the population mean, or average miles per gallon in this case.